So just a reminder that our homework 1 will be due on homework will be due on Friday. So I think last time we just stopped at the T distribution. Am I right? I know. Oh, sorry. I stopped at the sampling distribution, right? So I guess we covered this last time, right? This set of slides has been covered, and I think we've done this example. Did we? I think we did it, right? Right. So, okay. Let me check. Sorry. It's better to check. What did I done? Where did I stop last time? Statistical, right? Simple random sample. Okay. Simple random sample. But can you remind me when did I stop? Sorry, which slide did I stop? Because I really can't. This module class I can't recall. So thanks for letting me know. So basically I stop at somewhere here. Okay. So it's good to recall what we have been done so quickly. So what we have done is the starting point of doing inference is based on data. So we work on sampling distribution, and in in terms of terminology is where population, where it is studying the subject want to know. It's a big picture, and we are unable to know everything the big picture. So that's why we are trying to pick the small one. This is called the sample. And what the goal is trying to use the small sample to infer what happened in the big picture. So that is the meaning of sample and population. I add this slide because I think that would be useful to let you know what is a sample and population. And a random sample actually means a random draw from that, right? As a random sample, it's going to be representative. And we know simple random sample is have a feature that every element is being selected equally, and each element is selected independently. So it's a simple random sample. And technically, it actually means this: if they're simple random sample, actually they have the same. This random variable are independent, and they follow the same probability function, or the big F or the P are the same. And it actually means the mean and the variance are the same, and covariance 0. Okay. And in our class, the main focus is on the sample mean, although we will sometimes touch on the sample variance. And because the sample mean is later you will see is a good way Hi. Is it working now? Oh yeah, sorry. Do you hear me before or is it okay? Okay. So I don't know why the mic doesn't work, but good to see it works. So law of large number. And the next is central limit theorem, as I said, is when the sample size get larger and larger, right? And this sample mean actually goes to the bell curve. Okay. So the central limit theorem essentially said, right? Suppose we know the sigma square, okay, and you know the mu, then actually you will have this property, right? So the sample mean will have a normal distribution with mean same as population mean, the variance is sigma square over n. Okay, so that's why this normalized version is a bell curve. Okay, and we just know how to do the calculation. Okay, so we also know the binary data, right? It's either 0 or 1, right? And everything actually applies. Okay, except the fact that we don't have sigma anymore. Sigma is just sigma squared just pi times 1 minus pi. So everything that actually carries over. Okay, except the fact that now it's not sigma over root n, is rather than pi times 1 minus pi in the denominator. Everything the same. The only thing required is we need to have n pi times 1 minus pi, that is 5. I mean, that is not a restriction usually satisfied, right? So this is later you will see something we would have no problem of using in general. So probably we stopped here last time somehow, somewhere in the middle. It's we just know the central limit theorem, right? Is saying that right, this is the central limit theorem, right, in a graph, right? It's just like x bar minus mu over sigma over root n is exactly z is a bell curve, right? And the problem is we actually don't know sigma. That is the key issue here. So basically what we are going to do, right, is instead of talking about, we'll have a x bar over mu over s over root n, okay? And that will become a mean 0 again. And this is very similar to the z, but this is actually called t n minus 1, okay? So that is exactly what we're going to talk about, okay? So the main issue is when we don't know sigma, we have to use the sample variance. And when we do the sample variance, it's no longer a bell curve. It's very similar to bell curve. If you try to have a bell curve down there, the bell curve will look like this. The bell curve, it will have a smaller tail and a taller head. Okay, this is the bell. Okay. So the Z bell, as I recall, the Z bell is like this, and the T bell is much more higher in both tails. So that means that actually recall T is actually have a higher kurtosis, right? They're still symmetric, and of course the variance of T is larger, right? Is that okay? So that is the main goal of this part. So that is the idea behind this, okay? But it's a crucial thing is when we have to use this S instead of sigma, okay? If we do this instead of this, instead of sigma, we need to assume normal distribution, which we call normality assumption, okay? This is somewhat strong, okay? And the reason is if you don't go in this way, it's not easy to know how to do. Okay, so it's hard to proceed if we don't make some assumption there. Okay, so that is a assumption that we need to put there to make it work. Okay, and later we'll talk about how to make it work. There are several ways to check this one. Okay, And one easy way is you try to look at the data you collect, right? All the observation. You try to draw a histogram, right? If you looks like a bell, then probably yes, right? Or you have a look at the data. Is it going to be is it going to have a skewness? Check skewness. It's going to 0. Check kurtosis. It's going to 3, right? And this is the way you check, right? Because if the population is follow normal distribution, right? And that means the sample mean also the same, right? In this case, this is all the same, right? This is all the same, right? Because this implies this, okay? You can never check the population, right? But you can check the consequence of this assumption, right? You check this is whether this is true, right? I mean, of course, if you use the central limit theorem, this is true, right? But this is guaranteed. I mean, there you have to check, okay? Whether it's apply or not, okay? So if this is normal, the sample mean also normal, okay? Because the idea is, remember we learned in bell curve, right? This is adding the 2 bell, right? Remember the bell, 1 bell plus 2 bells, right? And actually is equal to the 3 bells, right? So you add many bells. If each of them are normal, adding n bells by n is still normal. Okay, so that's why this is following from central limit theorem. The key difference here is we don't require large sample, okay? Because central limit theorem require large sample. Now we don't, okay? So that is the same thing here, okay? So the only different thing is we replace it with this guy, and under normal, this is called with T, okay? And with n-1 degree of freedom, it is not clear why we would use T n-1. It's related to chi-square and relate to some math that we don't cover, but you just need to know that we actually have to use -1. And let's see the example and try to tell you how we can do it, okay? So this question is the following, okay? So we have a population, have a normal distribution with mean 5. So that is the normality assumption, okay? We need to have this for the T have to work. So we just, what we have here is like this. We have a bell curve here. This is, the mu is 5, okay? The population look like this, okay? So what we're going to do is we are going to draw 100 sample here. Okay, so basically just like we're going to draw 100 sample, 1, 2, 3, blah, 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 blah. We draw 100 out, okay? So with x1, x2 up to x100, okay? There are 100 data. And then we can calculate the sample variance, right? Which is 8, okay? How do we do about that? Because you can calculate sample mean, right? Just add 1 up to 100, divide by 100, right? And the sample variance just you calculate each observation minus the sample mean, take the square over 100, right? -1. So remember we have n-1 at the denominator, which we will explain after the break why we have n-1. Okay, we'll give the idea why you have n-1 instead of n. You become clear that n-1 is the appropriate concept to be used. Okay, but this is the sample mean. Okay, sample variance. Okay, so the question is, if you draw this, right, 100, and this guy is, because it's the bell, you draw a random thing, it's also a bell, right? And we know this is going to be 8 or 25 again. Okay, and I don't know which one we draw, right? But this is a bell. This is a T curve. This is a T, right? But this one it can be transformed to here, right? T, this will be 0, right? T will be 99, okay? T is equal to x bar minus mu. If we know the mu is 5, right? And S over root N, okay? N is 100, right? S is root of A, okay? So it's here, or them here. Okay, so, and now we know this is going to be T99, right? So the question now is like, okay, we ask, here is 4.5. Okay, what is the probability sample means less than 4.5? So it's like this. So we want to know this area, right? We want to know the probability less than 4.5. Okay, so before we do the calculation, so let's see why we want to do this, right? Why we care about this. Actually, this highlights the question what we're trying to do in the next month. Okay, next month we'll do in November. One of the questions is what we call hypothesis testing. Hypothesis testing. There are many ways to use this result. Why I want to know this property, but one way is to consider is hypothesis testing. Okay. So the question here is being like the following. Okay. You consider application like this. You are a quality controller. Okay. You look at the product you are going to sell. You claim the active ingredient of a product, food product, has mean of 5. Right? Or your auditor, right? Someone claim they have the product is like the mean is 5, right? On average, okay? For no normal distribution, right? And the problem is, okay, you collect a sample of 100, right? And turn out it is actually 4.5, okay? So let me repeat the statement. It's just a claim, this hypothesis is claimed by your client, claimed by the manufacturer. They claim it's 5, okay? And you collect the sample, actually it's 4.5, right? It's much less than what they claim to be. And then the question is, okay, is it 4.5 so less compared to 5? Right? The question is, let me repeat the question again, is we got 4.5, right? The question is it far off from 5? Okay? The question is, look at the statement, is it far from 5? Is it far from 5? Then how can we know far from 5? Look at the distribution, right? Look at this. Is it likely to be 4.5? Right? Because when you do sampling, then you actually have some sampling error, right? Because you may unluckily get this 4.5, right? Because okay, you got 4.5, go to the guy and say, okay, 4.5 is okay, say within some error, right? It's not error free, you just unlucky, right? Suppose you get many, then that should be okay, right? The question probably, okay, you call the other one is 4.6, right? Or 4.4. Then you go back to him, say, okay, I have 2 samples, and yeah, it's below, but okay, it's okay. You just unlucky 2 times, right? No matter how many times you talk to him, they will say, okay, you are unlucky. Then how can we say if you just do once, okay, or do many times, whatever? How can we say 4.5 is so low from 5? Okay, the idea is justified by saying that if the difference big enough, means that this area is very small. If this is so small, then you think some unlikely thing it happened, and that means your original conjecture, your window assumption, or your original hypothesis is wrong. Okay, so that will be covered in the next month. The main idea is you have some hypothesis, or some client or some manufacturer try to say something, and you have the data, and you try to see if the data you collect is due to it's very unlikely that to support your original claim. If this is too weak to support, right, then you would say, okay, I will not accept that it's 5, right? That's actually the Consumer Council, right? They do it, right? You just try to see if they say the food have active ingredient of 5 grams of, say, protein or whatever, vitamin or whatever, and then actually you got 4.5, right? And then you try to see is 4.5 below 5 enough, okay? Because as you can see, 4.5 and 5, how far they are apart depends on 2 parts, right? Actually depends on the sample size and the variance, right? If the sample size is very large, right, then the difference will be small to justify the difference, right? If the sample variance is also very small, then you also then your measure is very accurate. Some slight deviation will justify the distance. Okay, so which we cover in the next month. But that's the reason why we want to look at this. I hope I convince you this is something that we would cover, and this is something that is important. Why we care about whether the sample mean is far away or not so far away. Okay, and in that case, we know that's 5, right? So that's the reason why we would meal is not an issue, right? We can someone will give you the meal. The problem is you use the data to check whether the meal belong to the thing the data support or not, right? Someone tell you the meal, you collect data, which is X bar, you see whether X bar is far away from meal or different from meal, right? So that is the main thing we're going to do in November, okay? But now I guess I convince you why we need to find this area, okay? And how to find this area? Again, the same, you just transform the 4.5 to here, okay? By using this formula, okay? Minus the meal over this guy. So this is exactly what's going on here, okay? You minus the meal over 5 over 8 over 100, right? That gives you negative 1.768, okay? So then the next question is, how can we do this in Excel, right? This left-hand side area, right? So basically just T this, okay? Negative 1.768, 99, and then true, okay? This will be the T table, okay? Negative 1.68, okay? So let's see the Excel, okay? We'll show you this number. Okay. P dot this negative 1.68 and then 99 and then true. Okay. 99 come from the fact that it's n minus 1, so it's 100 sample minus 1. Okay. So this is the formula, as I have said, I've shown here. Okay. So this area is very small. Okay. So I think it's okay. So I think if you consider this is the case where you are told that the population mean is 5 and you collect 4.5, then in that case you would tend to say 5 is not believable because the area is so far away from that, and then you would try to say no. Okay, you would not believe it's actually 5. Okay, if you're Consumer Council, you see this happen, then you just go to court, sue the guy, okay, or just ask him to rectify this. Is that clear what we have been doing? Okay, but this is the kind of like the preview what we're going to do. So this is a knowledge that is kind of prepared to do the rest. Okay, it's by itself is not really we do not use it directly. Okay, these are some preliminary knowledge that we are going to do for the rest. Is that okay? Is that okay? Okay. If so, then basically and this part. Okay, we're done with the 4. Okay, so let's start with the estimation. Okay, we just give you a brief review, and then we have a break, and then come back. We talk about this. Okay, so estimation. Okay, so the goal of this is trying to estimate what we call population parameter. Okay, in some sense, it's something we're interested in certain thing population, right? And usually we call the theta, and often it is a summary statistics. Okay, mean, variance, kurtosis, skewness. Okay, for example, application, we want to know, say, income average of a city, variance of the income of a city, right? Or how much they spend on average. Someone want to know. Okay, so it's very standard. Okay, and we are trying to collect some data to make a guess out of it. Okay, and a systematic way to guess, okay, is called estimator. Okay, and in general, you can write down it's actually a function of a random sample. Okay, so basically is a function. That means that if you have the sample, you collect data, you have some formula, you get some number. That's estimate. It's a formula, right? It's a formula. So it would usually depends on the sample size. Okay, so that is we write this as a n there. So that's why, because sample mean, sample variance, both are depending on n. Okay, both depend on n. Estimator. And estimate is once you collect sample, you plug into estimator, that become an estimate. Okay. So just a graph is what we're trying to look. Okay. So that is what we have is here is our population. Okay. We have a bunch of data here. Okay. And you can imagine this is a village, right? Or a city or a country. There are many people. Each people will have some income, right? A cross means a guy with income. So we are interested in, say, average income, right? Meal or sigma square, right? So these are usually called parameter. Okay. And what we're going to do is actually we try to collect some data here. Okay. We take it out. Okay. This we randomly pick up something. Okay. We call sampling, right? Maybe I use the green color. This is called sampling, right? We do some sampling. Okay. And the case we focus on is called simple random sample. Okay. And in this simple random sample, the goal estimate is trying to estimate, say, this guy, right? We want to estimate this. Okay. How can we estimate this? We just have to do some way systematically from the sample to a number, right? So example is like the one estimator is called X bar is what we call the estimator. Okay. Because sample mean is a way to estimate population mean by what we mean sample mean is sum of all the observation divided by how many of those, right? Sample mean is a rule that sum of observations, right, divided by number of observations, right? Okay. This is a rule, right? This is a rule, okay? And and this rule actually gives a number, right? Give a number. Okay, a number to guess this one. If the rule give a number, actually this is called point estimator. Okay. If a rule is not give a number, give a bunch of numbers, an interval, okay? This is called interval estimator. Okay. So the idea is following, okay? You can imagine how it looks like is like this. You collect the data, you try to estimate, right? And it's like this. What you want to do is to have a, I don't know whether it's arching, right? So you want to hit the bullseye, right? If you have a pistol, you just hit once, okay? There is a point estimator. Okay, point estimator. It's one shot. Just give you a number, right? That one shot, boop, that's it. Okay. And what is interval estimator? Okay, interval estimator is like this. It's a rocket launcher. Okay, you just try to hit, you hit like boom. Okay, then that is called the interval estimator. Okay, it's like a shotgun, if you like, or it's like a rocket launcher, right? Or you like, it's like a bomb. Okay, it's a nuclear bomb. You just bomb the whole area. Okay, instead of hitting one point, hit multiple points. Okay, and that is something actually you see in the newspaper or TV, right? Every day you should try to look at the financial news. Okay, in the morning, the news anchor talk to the analyst, and you ask, okay, what would be the Hang Seng index or the stock index today, right? And usually they will say, okay, today maybe it will be 1500. Okay, 1500. Then there is a point estimate. Okay, what do you expect? Okay, today maybe we'll drop by 1000 points. Okay, then there's a point estimate. Okay, and if they say, okay, it will drop like 500 to 2000 points, then it's interval estimate, right? If they say today's Hang Seng index is going to be 1500 to 1600, give you a range, then it's called interval estimate. Okay, so there's something that we're trying to do. Is that clear? What do you mean by it? So the main thing we want to cover is the new thing is the new terminology is what we call estimator. Okay, and we have interval estimator and point estimator. Okay, and also parameter. Okay, and finally, get one point I forget to mention is called estimate. Estimate is a very simple definition. It's just once you have the estimator rule, right? Tell you how you can come up with a number. And if you collect data and plug into the estimator, you get estimate. Okay, estimate is the outcome of the estimator. Okay, if you have the sample going through the estimator and you get estimate. Okay, it's the final result. You can say estimate the final result, right? Final result. Or the output, right? Okay. This is the input is the sample, right? Input sample, estimate the process, right? So you get the input, you get the product of the process, and you get the output. Okay. So these are all the terms. And after the break, we'll talk about what are the good property of point estimator. And that's how we justify why with S square, it's a good to estimate sigma square. Okay, of course, we also want to justify why X bar is a good estimator. Okay, and the final thing is we're trying to tell you how to do a nuclear bomb. Okay, do an interval estimator. Okay, and and it's looking at the how to do interval estimator is later you see for the mean will be X bar. Okay, and you go left and go to right. Okay, and that is the point estimate will form the basis of what we're trying to guess, and then you go left and right, and that would be the main goal of today. Okay, I mean it's just the main general idea. Okay. Okay. Maybe a break of 10 minutes, then we come back. In the meantime, I go around to see if any question. Hi. So some of you worry about whether integration and differentiation appear. No, that is the we don't have integration and differentiation in this class. Okay, I mean that is technical thing. We don't need that. Okay, so some of you also worry about the final test. Is it going to be difficult? And I would say it generally, I think, is easier or similar level to assignment. I think it's easier to me. I mean, I think when I make it is tend to be easier. I compare the assignment and the test. So that is how I think. And so the main thing about today is, let me just quickly preview because after the break. So the goal is the following. So we have the population. Okay, we want to study this population. Say we want to know the mu and sigma, right? Because example will be, we want to know the income of a population, right? And then a city, right? Then we can decide what kind of product we want to produce. So suppose Apple, right? You want to see how much the iPhone should charge, right? Or you want to know, say, binary data, right? How many people would like to have a bigger screen or smaller screen? Whether people would want to have a flip phone or non-flip phone, right? So we want to know this mean and variance, right? And sometimes if you look at proportional data, right, you may also care about the proportion, right? And the way to guess this is to do sampling, right? We get some random sample, okay? And how can we guess this parameter, right? Is we have some estimator, right? It's the way to guess what they are. So we have sample mean and sample variance, right? And they are called estimator. And once the data you put in is called estimate, right? And there are two types of estimator, right? One is called point, one is called interval. For point, you just have a single point, single number there. Interval is more than one number. Okay, so that's a goal. Okay, so that is go back to definition, right? Estimate is a particular value. Okay, probably and a guess to what we want to do. Okay, so there are two types of estimator. One is called point estimator, give a number. Interval is give you the interval, right? So so let's get started with point estimator. And by this, we justify why we have x bar and s square as the estimator. Okay. So we will try to do it by justify saying there are three properties of good point estimator. We call unbiased, efficiency, and consistency. Okay. So let's see this one. Okay. What unbiased said is the expected value of estimator is exactly the parameter. So which means the expected value is equal to what we want to guess. Okay. That means that on average, we hit a target. Okay. Do note that it doesn't mean hit a target, but it on average hit target. Okay. So, and let's see what do you mean by this. Okay. Say, suppose the goal we want to hit is this, the bullseye, right? This guy. Okay. And the estimator may have this value, have this value, have this value. Okay. But on average, it's hidden target. Okay. By themselves, none of them is nowhere near the target. But on average, hidden target. Okay. So it's called unbiased estimate. Okay. So another way to think is like this. Okay. Suppose there's a guy. Okay. And suppose the guy want to date this dream girl. Okay. And he's unable to date this girl. Okay. Instead, he dates another girl and he also dates the other girl, okay? He dates this girl and he dates this girl, okay? But on average, he actually did date the middle girl, right? Although he didn't actually did it, but on average, he did it, okay? So that is the idea, okay? Or put it this way, there's an enemy, the tank is here, okay? There's another 10A, 10B, and 10C, okay? Okay? And you are the guy here, okay? And you actually hit this tank and hit this tank, okay? And on average, you're hitting B, okay? So you want to hit B, but you didn't do it, okay? But you add A and C, on average, you hit on B, which is the target, okay? It's not actually hitting it, but on average hitting it, then it's called unbiased. Is that clear? So it's a very weak concept, okay? And the idea is if we have do it many times, right? And there are many of them, average is hitting them, okay? So it's not hitting, it's nowhere, it doesn't talk about how close your guess to what you're supposed to guess, okay? But it said if you do it many times, average of your guesses will be the one you want to guess, okay? Let me repeat it is average of your guesses is going to be the one you want to guess, okay? But it say nothing about how good is your individual guess, okay? But you say aggregating many guesses, average of those guesses is exactly what you want, okay? It has say nothing about how close of each guess you have, okay? Is that clear? Okay, so that is called unbiased. But that means that it's very weak assumption, right? Because actually there's no way to talk about how the distance. Okay, so that is called unbiased. So to take into account of the distance or accuracy, that actually comes the new concept called efficiency. Okay, efficiency actually focus on the case where called unbiased estimator. Okay, so you have two type of method, okay, and both method actually would be unbiased. So means that on average is hitting the target, okay. Then can you compare them? Yes. The comparison is look at the variance, okay. A is better than B if A has smaller variance, okay. That means that both of them on average is hitting the target, okay, but A on average closer than B, okay. So look at the diagram and you will see, okay. So here we have A is like, let me use the blue color, it's here, here, and here, right? On average is in the middle, right? And B is here, here, and here. On average hitting the middle as well, right? And you can see A is more closer to the target than B, right? Both of them on average hitting target, right? So A is better, okay? A is more precise, okay? So that is called A is more efficient, right? Efficient in the sense that you can get a better estimate, right? Is that okay? So these two are something based on a fixed sample size, right? Or based on the idea of finite n. So we have another one that related to what we call consistency, okay? Which is a bit technical, okay? Actually, some of you worry about the calculus, right? So I guess this is the last slide that we say limit notation. Okay. But what essentially said is, if n is very big, n is very big, okay, this guy is this, Okay, so unbiasedness said average of our guess, average of estimate is actually the parameter. Okay, and consistency said when n is very large, we actually get what we want. Okay, so we don't need to talk about average of what we hit, but actually we hit it. Okay, so the idea is like this. Look at the graph. Okay, it's easy to understand like this. Okay, if the sample size is 1, is small, sample size is 1, is very small, it can be outside. Okay, and this is not biased, not unbiased, so it's biased because it's far away, right? And 2 is also a bias because somewhere here, right? And 3 is also biased. Okay, doesn't really matter, right? All of them are biased, but you can see as the sample size get larger, the area shrinks, right? And if you get bigger and bigger sample size, actually likely to shrink to this theta. Okay, and that case is cost consistent. Okay, let me repeat the statement. Originally, sample size 1 can be anywhere, right? Outside, right? Can be outside, right? Maybe somewhat here outside, right? Somewhat here, okay, somewhat around there. And when you get sample size smaller, it shrink a little bit, right? And you get bigger, it shrink further, right? At this, it's just like keep shrinking, right? Say below is like this and keep getting narrower and narrower. And at the end, this thing shrinks to exactly what you want to guess. Then it's called consistent. It can be biased. Okay, it can be biased. You know, this graph that I just drawn in the way it's biased. Okay, it's biased, but sometimes it's still consistent. Yes, because the sample size goes large enough, actually this goes to 0. So, okay. So we will use these several properties to evaluate what we have done. Okay. So the first thing is our popular friend, sample mean. This is something that we'll be using it all the time, and we have been using it, right? So there are many things here, but I just want to highlight several points here. First is unbiased. Okay. Second one is efficient. The third one is consistent. Okay. The first one is unbiased. Probably we know it very well, right, from last topic, right? We just covered already. That's the sample mean is actually the expectation of that is actually population mean. That is, I think there's no doubt we have done it. Okay. And the consistency is, we also know it that is set law of large number, right? We know it is when the sample size go large enough, it's actually same as population mean. So that is not. So we know these two facts actually from the last chapter. So what's new here is this guy, okay, efficient. Okay. And since the technical slide, I'm not going to go to proof, but the main proof is the following. The main idea is you can consider any weighted average. Suppose you consider any weighted average, okay? When you calculate other weighted average, okay? Other weighted average is also have the unbiased property, right? Because efficiency actually compared to unbiased estimator. Okay? In that case, we can show by using Cauchy-Schwarz inequality, okay, or there's some other many ways to prove it, but they will show the variance is actually smaller. Okay, so that's why we use sample mean. We don't use any weighted mean, right? Suppose you would want to use some weighted mean. No, we don't. Okay, we just use the sample mean. Simple sample mean, right? Because you would tend to think the following might be in your example, right? Suppose I have a data. I collect data is like 1, 1, 1, 1, 1, 2, 2, 3, 3, say. Okay. If this is data, you would probably want to give more weight to 1, right? Because 1 appears a lot of time, right? And simple mean, simple average, you just give the weight according to its appearance, right? It appear 5 times, it appear 2 times, it appear 1 time, right? So it's just 1 times 5 plus 2 times 2 plus 3 times 2, right? Over 5 plus 2 plus 1, right? This is the simple average, right? And if you think 1 appear too much, actually you want to assign way more than 5, right? Then it's a weighted average. But here it tells you that you should just use how many times appear as a weight, right? You should not say I put 5 square to weight, right? That is not efficient enough. Okay, so that means that some weighted average is not a very good estimate, okay, for a sample mean. Okay, but do note that it doesn't imply sample mean is not useful, right? Because the thing that we're trying to estimate is mu, is the population mean. Okay, if you care about the population weighted average, then a weighted average may be better. Okay, but the thing is, we only care about the population mean, so that's why the interesting thing is we use the sample version of it actually would works. Okay, I hope this convinced you why we use sample mean. Okay, the next one we are trying to say is what we have been working on. It's called the population variance, right? And you would wonder, actually from the primary school, so secondary school, right? Why don't we do this? Why don't we do this? Why don't we do this guy? Why we have to n-1? Why I don't understand. Okay, why we have n-1 instead of n? The main reason is turn out to be, okay, maybe usually I put this guy, sometimes they put sigma hat, but anyway, it turns out why we use this guy is because we will show in next slide, technical, but this is exactly this. Why we use n-1? Because n-1 is unbiased. When you use n, it's biased. Okay, that means that use n, you underestimate. Okay, let me repeat. If you use n, that actually is underestimate. Okay, so that means that this guy, if you use this, if you do this, as I said, right, it's actually less than this guy. Okay, you basically do it by n rather than n-1. Okay, we'll try to explain why you underestimate, but that is the main reason why we talk about that. Okay, but I think actually both of them are actually consistent. Okay, both of them are consistent, and so that's why it is okay. Okay, it's not that bad. Okay, it's not that bad for use this one. Not that bad, in fact, especially when n is large, they are the same. Okay, but when n is small, we have to be very careful. Okay, so that's why we still use this guy, because a lot of time we don't have very big n, then this one will be the appropriate one. But when n is large, there's not too much difference. Okay. So let me, if there's no question, let me try to give you more idea why this is the case. Okay. So the main key point, as we see here, right, is this guy. Right. And that's the reason why we have n rather than mi. That's why we call this sample variance in Excel or in other software. So let me give you an intuitive explanation for why we have this. Okay. The very main reason you have n rather than n-1. Of course, you can actually prove it, right? That is the thing up here in the slide. Okay. So there's a formal way to prove why this is the case. The main reason, you try to look at the proof, is the reason this is an estimate. Okay. Suppose we know mu. Okay. And if that's the case, we should still use this. Okay. The main reason why we have to use n-1 is related to we have to estimate the sample mean. Okay. What is the reason behind? Okay. Intuitively, S or sigma, right, is capturing how the data is different from a sample mean, right? So the main idea is the following, right? You collect data x1, x2, xn, right? The question is how these data are different from the sample mu, right? You look at the distance between the two, right? And square, right? You do the same for everyone, right? That is how you would estimate, right? But now you actually don't have this guy. You don't have this guy. Okay? You actually have this guy. Remember, the sigma is measuring how each element differs from the mu, right? And the more variation, more fluctuation between this will bring you a higher variance. Okay. Now the question is being the following. You have to estimate this guy. Okay. The main problem is how you get this x bar. Okay. You have to, x bar is coming from the average, right? x2, xn-1, xn divided by n, right? So it's just adding up divided by n, right? So actually, you calculate this is coming from the data, right? In the other words, when you calculate the distance, now you calculate the distance between this and this, right? For each one. Okay. The problem is if you have only the changes of the first n-1 only matters. The reason is if I know x bar, I know the first n-1 guy, the last one is fixed. Right? Because of they have to satisfy this equation, right? X bar comes from the n data. So if I have to guess x bar, actually the variation to us is just n-1, because if you change all this is already fixed, right? Because this one have to change according to the relationship. Okay. So that's why you see some textbook would say this is called degree of freedom. The reason is once you guess this guy, x bar, they're not n good distance. There's not n distance of each data because you only have n-1 distance. Right? The reason is if you fix the n-1 distance, the last one already been fixed. Okay? So that's the main idea. I mean, which is not easy to understand why that's the case. Okay. And there's a math behind. And I remember when I studied this, first learned this, I spent a month in the library to figure out what's going on. Okay. Because the elementary textbook doesn't explain to that. Okay. And they try to say degree of freedom. And I never understand the concept of degree of freedom. Okay. But turn out, if you look at the proof, it's very simple. Turn out to be because of this is random variable. And turn out that its variation is less. So that's why it's n-1. And this degree of freedom actually is a pretty useful concept in the sense that later you will see when we try to estimate variance, okay, this denominator n-1, okay, and in general is n-2, n-3, n-4, n-5, and how many you subtract from actually depends on how many things you have to estimate first. Okay. In this case, we only estimate the sample mean. So that's why we -1. And if you later you look at the look at regression, look at ANOVA, you will see the more parameter you estimate, that means that you lose the degree of freedom because you estimate that they actually give a constraint, and that means the variance is actually less than what it's supposed to be. You underestimate. In general, it means that when you have the system has much, you estimate certain things, the variance has to be lower. Okay, but I mean this is way advanced than what we cover, but just it's a puzzle. Okay, for those of you who still puzzle why, it's okay, keep your puzzle. It's hard to see why they are true. Maybe when you first learn it. I mean, I told you I spent a month in the library to figure out, and in that time there's no internet, or not at least the internet is not that, there's no Wikipedia, but I hope I convince you somehow this is right. Okay. Now, the next part is very simple. A special case. Okay. For binary data, we know the sample proportion is sample mean. Okay. So sample proportion is a good estimator for sample mean, right? So population proportion, because this is unbiased. Okay. It is also efficient. Okay. And it's consistent, right? So that is three good properties there. It is inherited from sample mean, right? Because it's only, the only thing changes is only data change, right? There's nothing related to what happened, right? Only say now we just take the value of 0 and 1. Okay, there's nothing new in this context. Okay. The only thing new that we are trying to do here is, okay, this unbiased we covered already. The only thing new here is the population variance like this guy, right? So how do we do sample variance? Right? Shouldn't we have 1/n? Some adjustment n/n. Should we do that? Should we have this guy? Okay, because this should be the unbiased one, right? Unbiased. Okay, so we use this guy. In general, yes, you should use this guy, but in actual practice, we don't. The reason is because when we do binary data, usually n is big, right? And this guy tend to make little difference. Okay, so that's why we just basically skip this guy. It's no problem. Okay, so this is a bias, but in general, it doesn't cause a issue. So for simplicity, we just use this guy. Okay, so there's no particular reason why, but just this is a good one because this is still consistent. Okay, all right. Although it's biased, but it's consistent, so that's not a problem. Okay, that's not a good problem because with usually the binary data, right? Usually it's big enough, so it's not an issue. Okay, so that's why for in general we have to do n-1 thing, but for binary data we don't, because it's still consistent. It's not a big issue. Okay, so the same apply here. We just the variance of that, right? The same thing here. Now, we have interval estimator. Okay, so now we have done suppose you give a date, you're given data, you try to guess what happened to the mu and sigma. You know how to do it, right? We told you just do the sample mean and sample mean and sample average, sample mean and sample variance. Okay. So what left is trying to guess is what we call the interval estimator, right? Instead of a point and shoot, we use a nuclear bomb, right? Or a grenade, right? So how can we do it? Okay. And now the main thing is we need to rely on what we call normality assumption. Okay. And the main idea is we know this is a good point estimator, okay? But we really can't go one more step without knowing how X bar looks like. Okay. So, but we know that two things that we know X bar looks like, the sample mean, is either if X is normal, the population is normal, or large sample, this thing will hurt, right? Either central limit theorem or normality, okay? Then we would have this. Okay, is that clear? That we just learned in the previous topic. Either you invoke central limit theorem or we use normality assumption. Okay, is that okay? So this is we were bell. This is just to remind you. This is a bell. Just mean this is bell curve. Okay, this is mu. This is sigma square over n. Okay, so that is the main thing. Okay, and this come either from central limit theorem. Okay, if you don't want to impose anything on the population, or you just go directly to make this assumption. This is strong, but this is for our case we have been using. Okay, I mean that is for this class that we'll be using this normality assumption almost all the time. Okay. Okay. Later you will see we have to make assumption one way or the other. Now, the question is, because we know X bar is so good, right? So that's why I'm talking about interval estimator. We really want to say is to have a symmetric interval. Okay, so basically just like the following. Let's see. This is the mu, okay? And maybe we get X bar is here. So what we want to do is to go left and go to right, okay? Trying to see if this mu is included, right? Or putting it this way, it's like this, right? We have a normal is here. Okay. It's a bell curve, okay? So what you're going to do is we will have a doing some sample mean, and actually suppose the sample mean is like here. Okay. This is a good point estimate, right? Good point estimator. Okay. So our estimator go in this way. Interval means I go left by m and go right by m. Okay. And basically just like this is my guess point. I go left by something, I write something. Okay. And interval estimate would be saying that I have high probability that this interval, right, I will actually include mu. Okay. The probability that this mu is actually plus m minus m. M is the distance, right? It's very high. Okay. And as you know, normal extend to infinity, right? So this go to infinity, right? Go to the very end. So this high cannot be go to 1, right? If you go to 1, then m will become infinity, right? Because left and right go, there's no end, there's no ending point, right? There's no way you can for sure to put them together, right? So this probability usually we call 1 minus alpha, and alpha is usually 0.1, 0.5, so 0.05, and 0.01. So these are the 3 usual value. So basically you are talking about the probability that include the mean have 90%, 95%, or 99%. Okay, you want to have a high probability that once you do it, there's a high probability you include it. Okay, is that clear? So that is a goal. Sample mean, I go left by right by some m, and with good probability, high probability that they will include the mu. Okay, and then we will define what is m. Okay, of course the m, how you draw this depend on how the shape, right? Suppose depend on this sigma root over n, right? If sigma over n is big, right, your arms will be bigger, right? If sigma is very small, right, then the arm need not be that big, right? Because sigma over n, how spread they are, right? So that is the main goal. Okay, so which we will prove very quickly. Turn out to be the size of the arm is like this. Okay, looks a little bit tricky, but do note that this is just coming from this guy, right? To the square root of this, to the square root of that guy, right? Because remember the variance of this is sigma over n, right? You take the square root, the standard deviation. And the next part is this guy. And you ask what this guy is just this. If you remember the definition, this is saying the standard normal, right? This is 0 here, right? If you have symmetric, if this is 1 minus alpha, okay? And if this is alpha over 2, and this is alpha over 2, okay? And this, the number is z alpha over 2, and z alpha over 2, okay? So that's actually what we're doing, right? Because later you will see why why we have this one, okay? Why this one. The proof is actually very simple, so we just try to go ahead because I think this methodology is very simple, just few lines, so don't worry. So let's see the okay. Let me before proof, I just mentioned this before I go to proof. The proof is very simple, so don't worry. Just a bunch of several line there. Okay. So that's we say this is guy we call confidence interval estimator. Okay. So we just start from the sample mean, and you will have this guy we just cover, and this m is called marginal error. It's a definition, right? Because X bar, you go left and right, okay? That's ME. Okay, this. Okay. And go left and right by M, right? This is X bar plus M, X bar minus M, right? This distance is called the width, okay? And the highest number is called the UCL. The lowest number is called LCL. Okay, so let me should I go to the proof? Maybe I go to the example first. I mean, before next time I go to the proof because I think the time is rather limited today. Okay. So that is the formula that we're going to do. Okay. So we have a standard deviation, okay, which is 4, okay, and N64, and sample means 3. Okay. So 3 given this data, if I try to guess the mu, what should it be? We know the sigma already, so we got to guess the mu. And the sample mean we know is a good guess, right? So if you just ask, okay, what is my guess on the mu? I would say 3, okay, because that's the best guess I can get. Okay, it's unbiased, so I will not say it's more than 3 or less than 3 because they're equal likely more than 3 and less than 3. Okay, so the question is, if I have 3 here, right? So can I say more, right? Is it likely to be how likely is the mu? Okay. Turn out we do a calculation. Turn out to be between 2 and 4. Okay. We have a very precise saying statement saying that if we are going to repeat this process to many this kind of interval, okay, and it would likely to be between 2 and 4. Okay. But let's see how we calculate this margin error as 1. Okay. It's like 3 and we go left and right. Okay. It's more like 0.98. It's more like go left and go right by 0.98. Okay. How can we prove that? The formula is just Z alpha over 2 sigma over root n. Okay. And sigma actually come from 4. Okay. And n come from here. Okay. And you ask the last guy, what's this guy, right? This guy is just, remember alpha is the right tail, right? It's here. 95%. So the middle is 95, right? 0.95. The area is 0.025, right? This area and this area is 0.025. Okay. So that's why you go to Excel, will be the norm S inward 0.025. Okay. So that will give you 1.96. Okay, because actually we know how to do it because that is basically the empirical rule, right? 90 exactly the not close to 2. Okay. So that is, when we plug in the data, this tells us, if you ask me to guess what is the sample mean, population mean, I have confidence at 95 that actually is between 2 and 4. Okay. I would guess the best guess to me is 3. And I would say if I guess it's between 2 and 4. Okay. And of course, then narrow the interval, that's better, right? And you can see if I have bigger n, this interval you will shrink if everything remains the same. Right? So if I get a larger sample size, I get the same result. Actually, my guess, I will have the same sample mean, but the interval, I will confident that is more likely to narrow, right? So basically, you can imagine that the interval estimate actually tells you how precise is your sample mean, right? If it's narrower, actually you have high confidence that it's going to be good. Okay, so I guess I should end here because it's over time. So we will do this again next class to finish this topic. Okay, so it's not easy to understand. It's conceptually complicated for how to interpret this. We'll talk about the next class.